warm welcome, everyone, to our webinar on thermal simulation of high power density electronics. Thank you very much for joining us today. My name is Paul Lethbridge, and I'm the Director of Product and Solutions Marketing here at Simscale, and I'll be your host today. Today's presenter is Matt Bemis, a Senior Application Engineer with Simscale, specializing in modeling and simulation of electronics cooling, turbo machinery, external aerodynamics, automotive, and biomedical. He holds a degree in mechanical engineering from the University of New Hampshire. Let's take a look at today's agenda for the webinar. So over the next 30 minutes, we'll start with a brief intro to Simscale if you're unfamiliar. Then we'll get into the live demo of the thermal simulation, and we'll wrap up at the end with a 5-minute Q&A session and your next steps to try Simscale for yourselves. Please use the chat panel to say hi, and also feel free to ask questions there. There is an option to send it as a question, or you can just use the regular chat function to send your question in. And a reminder that your microphones will remain on mute during the presentation. So first, a quick intro to Simscale. In case you're not familiar, Simscale, we make high fidelity engineering simulation software, and importantly, we make simulation technically and economically feasible for you. There's a few points on this slide. The key ones, the key takeaways that I want to make here are we make simulation accessible at any scale. Simscale is powered by the cloud. We enable engineers to simulate without compromises. There are really no limits on the complexity of the models. We also deliver best-in-class solvers and UX on demand. Platform you'll find has streamlined workflows paired with high fidelity physics solvers. So now I'll hand over to Matt.
Thank you, Paul. So today's analysis, we are going to look at a natural convection work light. This is an LED system that has quite a bit of high power density and relies on natural convection. There's a few air volumes here. You'll notice there's one internal fluid volume on the right side. And this would, of course, be in an outside environment where most of the heat's going to the heat sink on the back of this. These are actually watertight. So a lot of times these are used in industrial applications where there may be a lot of dust or other bad things which can get in the case and damage the life expectancy of the LEDs. So in this case, it's watertight. You will see a gasket there, and that's really holding in heat, but we'll look at how the system performs later on. Just a bit more information about the layout. So we have some bolts on the top here. Most of the body is aluminum, including the back heat sink and sort of housing, as well as that front plate on the right in the dark gray. The chips for now are silicon, and the PCB is, of course, some layers of FR4 and copper. We're actually going to do a design analysis comparison. So you'll notice between design 1 and 2 here, on the right, the back plate, or I should say base plate thickness of the heatsink on the right is much thinner. So I've actually reduced the size of that, hoping for better conduction directly through from the PCB to that back heatsink to allow for better thermal performance. Here we just see a zoomed in cross section here. So on the right, the base plate thickness is 1 millimeter, whereas on the left, it's almost 2 millimeters. Now, one last item here. So we're going to not only evaluate the performance of these two designs, but I'm also going to show you a few new things within Simscale. So we're particularly actually going to look at our new immersed boundary method solver, as well as understand our new CAD associativity with Onshape. This really makes natural convection analyses like this for electronics much easier. To me, these are two big differentiators. So at this point, we can go ahead, jump out of the slides, and I'm actually going to start looking in CAD for a moment here. So I happen to use, internally, we happen to use Onshape. And I just want to go over a couple of the differentiators that this new IBM solver we have allows. Dropping in a quick cross section here, you'll notice a couple items here. So first and foremost, I have preserved the fasteners. In this case, we don't see any threads on them. However, we do have gaps. So zooming in, this is the exact type of thing which exists in manufacturer-ready CAD that can cause simulation problems. So often, and by the way, we also have a gap between the gasket and the outer casing here. Items like this, usually using a traditional CFD solution with a body fitted mesher, we would end up getting poor mesh quality due to the gaps, and we may either have to spend a lot of time in CAD defeaturing geometry, or we may get a simulation which diverges due to poor cell quality. So with the IBM solver, we don't have to worry about this at all. This is just no longer an issue. We don't need watertight geometry. We don't need to close small gaps. Instead, we can iterate very quickly on different designs and really get design insights. Just the last thing here, the chips are quite defeatured in this case. I sort of had already done this, but this is the IBM solver allows you to leave that detail in. So whether you have pins on the chips or so, those are items you can leave in. So let's jump over to the Simscale project. And I just want to mention here, the CAD associativity I'll show you today will be done via the Onshape CAD connection. So instead of downloading CAD and then uploading it to Simscale, we hooked up the two cloud-based systems via CAD connection. Now, just a housekeeping note, I had actually already brought these geometries in. So Webinar, this third geometry, has the wall thickness 1.92. Webinar 2 has the wall thickness of 1. I'm going to show you what it takes to actually create this simulation to set up. Then we'll go ahead and look at some results later on. Now you'll see a few different options here. If you've done electronics cooling within Simscale, you are probably familiar with our traditional conjugate heat transfer solver here. This is an excellent solution solver. However, you do need to defeature that geometry, worry about those small gaps and cracks because we use a body fitted mesher. Instead, for today, we're going to use the immersed boundary solution type. This is in beta, and this is actually something you can try out on our community plan. So it's in a public beta right now. I've used it for some time now and really enjoy it. We'll create a simulation. And the simulation setup, if you're familiar with Simscale at all, is we just work down the tree here. Under model, I have mentioned this as a natural convection case, so I want to set my gravity vector here. All I'm saying is down on the screen is the direction of gravity. Now, what's interesting for the fluid definition, this is actually where things get a bit different than, say, using our CHTV2 solver. In this case, we don't need to go into CAD mode and extract the flow volume or imprint our geometry or anything like that. Instead, I'm just going to rely on a geometry primitive here and start to make my bounding box directly from within the fluid assignment for the IBM solver. I'm going to size this really just based on best practices for bounding box size. And I think that pretty much looks good. So again, if your bounding box is too small, it can affect your results. You won't capture the thermal plume above the electronics. You'll tend to overpredict temperatures. So we've assigned our air fluid here. And next we'll start working on the solid material assignments. One sort of sneak peek you can see here is that Simscale supports a customizable material database now. You'll notice this is actually a company database. So we say Simscale just because I'm an employee, but you could generate your own where if you have 4 or 5 Simscale users, you could all leverage the same database. For now, I'm just going to keep using the default here. And I'll go ahead and assign the bolts. We'll work on the glass and gasket after. So next I'll do glass. And I will just hide a few of the larger bodies here so we can start to work on the details on the inside. Now, next I'm actually going to create a custom material here. So I'm going to just choose a plastic, but I'm going to be defining my PCB here. So what is very helpful that Simscale supports is we support orthotropic material properties. In this case, we care about thermal conductivity. So you'll notice at this point, we have a thermal conductivity definition for each Cartesian plane, so X, Y, and Z. Now, this is very important because based on the layers of FR4 and copper, the material properties change based on direction. So actually in the in-plane direction, in this case, looking at the Cartesian coordinate system in the lower right corner, X and Y, there's very high thermal conductivity. A lot of times it comes out to around, say, 20, whereas in the through direction, it's much lower, maybe closer to 1. Now, if you're curious where I got these values, it's really just summing a resistance or a thermal conductivity in series versus in parallel. Lastly, I just need to add a density value here, and we're good on that assignment. Just one last material assignment left, and we'll go ahead and move on to boundary conditions. Now, you'll notice there's no place to define inlets of the bounding box, temperature, and so on. So we're treating all those surfaces as essentially, of the bounding box, essentially open boundaries. And if you would like to modify the ambient temperature, you would just do it under initial conditions here. I'm happy, this is just really room temperature, so that works for me. Under advanced concepts is where we would define our power sources. So at this point, I have 3 watts on each one of these chips. Excellent. Lastly, I really think that's about it for the simulation setup. So under mesh settings, I did modify these settings a little bit. And lastly, it's an optional step, but I do like setting up result controls. And so what this does is it actually will give me a plot of iterations versus temperature on these chips. So this is really how I judge performance of my 2 designs. And at this point, I'm pretty much ready to kick off the analysis. So I can start this simulation. Now, I already have run this, of course, but next I'm sort of going to show you how our associativity works. So if I had made some design changes, or if I want to consider multiple simulations at once, it's not fun for an engineer to have to sit in front of Simscale and have to reassign everything. In this case, that step can be completely skipped. So I'll come to the geometry node here, select the webinar 2 geometry, select OK, and we can see right here, everything in the simulation tree here is preserved. So our solid material assignments are still preserved. Fluid definition, of course, even the power sources and result controls as well. So there's really nothing else for me to do here. I can actually come down to simulation runs, start this simulation, and I'll wait for an email when these simulations finish up. Just a couple other notes here. There's no limit to how many simulations you run. So right now I'm comparing 2 geometries. You could compare 10, 20, 30, it doesn't matter. They all get their own instance in the cloud. They all run in parallel, and you'll get an email when the simulations have finished. Now, as a Simscale customer, if you get stuck at any point along the way, you can leverage our in-product chat in the lower right corner. So we staff this with simulation experts. So these folks mostly have mechanical or aerospace engineering backgrounds, have been using Simscale for a long, long time, and can help you in real time on your project. I actually come from a background in the support world, and this is a much faster way to get up and running versus going to a support portal, filing a case, hoping it gets picked up, and then working from email from there. So lastly, if you want to temporarily share your project with the support team, all you need to do is check this box down here. This will allow us to take a look. A lot of times, instead of sort of guessing, if we just see your project, we can pick out what's wrong very, very quickly. So anyway, I think we can enough with the support section here. Let's go ahead and take a look at some results. First and foremost, I think it's worth just checking out the area averages here. So these are great for two different reasons. Number one, I actually sometimes don't even look in the solution field at the results. If I'm just interested in, is my chip temperature acceptable or not, I'll rely on these. It also, and it helps you just get that quantitative data instead of qualitative. It also helps you with convergence. So on the x-axis here, we actually see iterations, and we can see that my simulation wasn't converged until, let's say, maybe 800 iterations out or so. So it was varying earlier on. Towards the end, it's really not changing as we add iterations. So I know my solution is converged and I can trust it. Now, just one note here, it looks like I've got 3 probes. They're pretty much all the same temperature, and I've got 376 Kelvin. It's about 103 degrees Celsius, certainly on the upper bound of acceptable based on most design conditions. So remember that 103, and let's go ahead and take a look at my design 1 run here. And so looking at the same area averages, we can see I'm up to almost 420 degrees Kelvin. So that's about 147 Celsius or so. So as really expected, thinning up that back wall of the heatsink, the base plate, really allows a dramatic temperature drop here. Ultimately, even with aluminum being a pretty conductive material, the wall thickness was just way too thick and was keeping heat in. So now that we have some insights, let's go ahead, jump into the results and solution field and take a look at some of the other visualization you can get out of Simscale. Now, I had already done some results interrogation ahead of time. So I'll just sort of give you maybe say a bit of a sample about items which you can pull out of Simscale to have design insights as a thermal engineer. I'm going to start with this cutting plane. So the first thing I do when I run a CFD analysis of a natural convection case like this is I want to understand what the thermal plume looks like and look at the velocity there. In this case, I've turned on, so the color scheme here is looking at velocity magnitude, and I've turned on vectors to understand directions. This looks pretty much as I would expect it. So we have a large thermal plume above the light. I'm sure everyone here has experienced if they put their hand over an oven or a warm light, you can feel a thermal plume, and that's exactly what we see here. A lot of times, natural convection cases, I tend to see them in the, let's say, 20 to 50 inches per second velocity. This is right in that range, more or less, as expected. And we can see the vectors on the side. So the flow is both coming from the side walls, which are open boundaries as well as the bottom. So this is kind of a sanity check, I'll say, as to what I would expect. The plume is in the same plane as gravity, right? It's going straight up and down. It's not to a side, which would be a little suspect. The next thing I do is look at temperature. So here we can actually probably drop down the legend here, because ultimately not that much temperature comes off the electronics. So let's say maybe 12 inches above the light here, we've got about 32 Celsius. Now, moving on, it's pretty common for designers to have safety limits on temperatures. So for example, a thermal engineer may have a spec that says they can't place the light within 40 centimeters of a wall if it's over 35 degrees Celsius. So in this case, I'm using an ISO volume to actually visualize where in the model we have a 35 degree plume. Of course, higher than this, the air will just be cooler. Closer down, closer to the electronics, we'll see a warmer temperature. Now, in this case, I actually did not vary the number of fins. However, in a previous case I did on a similar project some time ago, I understood the difference of performance between a 9 fin design and a 15. And I was able to do that by using an ISO volume. So in this case, I said, hey, Simscale, show me everywhere. I'm leveraging an ISO volume. Show me everywhere in the model that's between 4 inches a second and higher in velocity. And I can understand if I have good speed through the fins. Now, ultimately, you can see here, we do get blue in between all the fins. That means there's good velocity going by this model. Ultimately, that's going to indicate good convection and a high performing model. I did an analysis where I actually stuffed in more fins, and that actually ended up choking the flow and making the performance of the design worse, which is a pretty interesting insight. Lastly here, I like to use particle traces to just understand the path of the flow. So I set these up below the model here at the base. They all come up, mostly go through the fins on the back. Some go around the front of the model here and then exit the top here. Again, these are just indicators that my results are good and the flow I see here is physical. Now, 1 or 2 notes, any of the visualization I've shown you so far can be extracted. So I can actually export a PNG here. You'll notice on the left, I can define the resolution, leave the background as empty, so you can download this, put it over an image you may have. And we can also animate the particle traces as well. So if I wanted to download a GIF or an MP4, we could go ahead and download both of those here. All right, so I think that gives you some insight into the solution and how you can get results out. You'll notice these 2 runs are still going, but I think at this point we can jump back into the slides here. So let's go back, and for summary here, we can actually see, so my design 1 was actually showing me temperatures of almost 147 degrees Celsius, whereas by just thinning up that back wall, actually significantly thinning it, we're able to drop about 42 or so degrees off this. So that's a very efficient gain. I mean, it's not often you can drop this high of a temperature off it, so that's excellent. So I think that's mostly what I wanted to show here. I think Paul and I can transition into the Q&A portion for now, and if there's any questions so far, I can answer them.
Brilliant. Matt, thank you very much. Excellent demonstration. And thank you, everyone. We've had a few questions come in and some interesting chat. So yeah, we have about 5-6 minutes left for some Q&A, as Matt mentioned. And what we'll do is I'll pick out a few questions from those that have been submitted. And Matt, if you're game, I'll let you answer them and take it from there. Is that all right, Matt?
Yeah, absolutely.
Brilliant, brilliant. Okay, so let me see, what have we got here? So I just go from the top down, I think, probably best. So does the IBM solver enable me to skip defeaturing my integrated circuit chips? For example, usually when I do a CFD analysis, I have to remove chip markings, pins, and so on. So basically, you know, how much defeaturing is needed?
Yeah, that's a great question. So luckily with this IBM solver, really our goal is to have the end user, the thermal engineer, no longer need to spend time on defeaturing. So we've known for a long time that is really the most expensive portion of doing simulation on electronics. It's not so much anymore because we're cloud-based, the runtime, for example. But removing those pins on the chips, removing those ID numbers and letters is time consuming. So in this case, you can leave it all on there. It's fine if your geometry has interferences or tolerance issues, no problem at all. And we just can run the analyses and go with it.
Excellent, Matt. Thank you. All right, questions coming in thick now. This is great. Thank you, everyone. How many core hours were used in this analysis?
Yeah, it's a good question. So I think for this analysis, I used about 40 core hours. So it's based on the mesh settings I use there, but ultimately the background cell count usually ends up staying pretty low because we are not capturing that very, very small detail, like the gaps between the gasket and the housing, like I showed earlier. So these are less computationally expensive than your normal CHD simulations you'll run for electronics within Simscale. So if you have experience with that, certainly know this will be much less in core hours.
Great. Okay, good question coming up. Does this new solver, IBM solver, provide transient analysis that was not available with Simscale CHT?
Yeah, that's a good question. So this IBM solution does not support a transient analysis, but that's something we'll support in the future. So in the future, I can't say when exactly, but not too long from now, we will support transient for both the IBM solution as well as CHTV2. So I'm looking forward to that.
Thanks, Matt. Great. Okay, what about the air temperature between the back of the screen and the printed circuit board and the chips? Does the IBM option automatically fill in the fluid?
Yeah, that's a good question. So I think what this person is asking about is the internal flow volume. So between the chips and the glass, essentially.
Yeah.
So when I put that geometric primitive in, around the model, because that primitive is inside the electronics box, we actually know it's air in there. So Simscale's smart enough to automatically define a fluid volume, automatically assign it as air as well, which is nice.
Brilliant. Thanks. Thanks again, Matt. Uh, just a question on the browser. So some sharp-eyed people noticed that this is all being done in a browser. I think I mentioned that at the beginning as well. So what browsers are supported?
Right, so I happen to use Chrome. Simscale supports both Google Chrome and Firefox, Mozilla Firefox. So you'll be good with either of those. Yep, I happen to use Chrome.
Thanks again, Matt. And I think we have maybe time for one or two more questions here. Does the SimScale CAD associativity with Onshape work for all simulation analysis types?
Yeah, it's a great one. So it does, as long as you are using Onshape, the associativity there should be consistent and really work great. I mean, I've been using it tremendously for our structural analyses as well, where it's common to iterate quite often within CAD. So it doesn't matter the analysis type.
Brilliant. All right, we'll have one more question, I think, Matt. Does the IBM solver support forced convection CHT analysis? So obviously this is natural convection. Can you put a fan in there or some other forced mechanism?
Yeah, that's interesting question. So we are working towards that direction. So this is still in a public beta, and ultimately we want our thermal electronics customers to be able to do both forced convection and natural with this solution. So we did natural first, but actually under a feature toggle, you could try forced convection. So we would expose boundary conditions and allow you to focus on internal flows. If you are interested in trying that out, please just email us. You can email product@simscale.com, and we would be more than happy to turn it on for you.
Excellent. All right, Matt, I think that's it for the questions. So let's transition to the last slide. Thank you, everybody, for some great questions and good feedback. So yeah, I'm sensing that many of you found the webinar pretty valuable, and hopefully you're keen to try SimScale for yourself and explore some of these new features. Matt gave you some direction just then. Just to reiterate, you can just sign up on simscale.com, and you can even request a one-on-one demo. You can contact us directly at sales@simscale.com, and you'll get a response from an application engineer, usually within 24 hours. And if you're lucky, you'll get a response from Matt. Also, what we'll do, of course, is a link to a recorded version of this webinar will be made available to all participants. So that should help if you wanted to listen to this again, or if you've got some colleagues that couldn't make the webinar and you just want to, you want to spread the good word about the Simscale simulation capability. So with that, we're right at the bottom of the hour. So I want to thank you all very much for attending. And this brings us to the end of our webinar today. Thank you.